Okay, good. So I guess we can start. Let me just see. Okay, so I guess people started a lab. So that's some real hands-on. So I did post stuff on Piazza. The plan is to get checked off after every lab section, as we said. So you really have to do the lab. That's kind of the crux of the course, is some stuff we do here in terms of theory and also homeworks, midterm, but lab is really where you will learn a lot. And that's why the requirement is that you do pass the lab. So you have to get checked off on all things. You don't have to get perfect score on the lab report, but you have to get checked off on all sections of the lab, and you have to also turn in the project, which is lab 3. So these things are kind of mandatory, so if you want to be in this course. So okay, with that out of the way, I mean, we'll try to be a little bit more lenient on the homework during these lab weeks, so hopefully that helps. But we're going to dive a little bit into the unbalanced differential amplifiers. We sort of already touched a little bit on this at the end of the last lecture. We had a structure that was, kind of, I guess, 2B was loading diff pair with current mirror. Active load. And this one breaks things a little bit simply because we no longer have this symmetry that allowed us to nicely do the bisection, just like when we were loading each leg of the amplifier with a resistor or even with active load that was completely symmetric. Right, so in this case, we said we would use the current mirror say this is VI1, VI2, and then this is VDD, and we're taking the V out from here. So we're using the current mirror, kind of map the signal, whatever's happening in this leg, to map it over to this one. So intuitively, okay, and well, I'll do this for the this sort of works a little bit, and it's kind of easier to think about for the differential signal. You still sort of have the symmetry, or at least you can slightly neglect the asymmetry if VI and VI1 and VI2 are the opposite signs. And so in case where, so this is VIC plus VID over 2, and this one is VIC minus VID over 2. So in the case where we're looking at differential gain, sort of from differential input to this output, I can sort of pretend that this point over here is still around 0. Okay. In other words, I can also kind of say that RSS is kind of like really, really large voltage. So all my current flows this way. There's multiple ways to interpret. In the book, they're like really detailed about it. I'm going to try to simplify it a little bit, but this type of circuit does have a little bit of a derivation to be able to understand really what's going on. So let's go out and write out the small signal model, and then we'll see what we can sort of neglect and what we don't. So before I do that, if we just looked at this circuit and I said, look, maybe I can ground this node over here, right? If I do certain approximations, if I forget the R outs of these two devices, if I ground it, then what's really happening is differentially, this voltage over here, actually, can you see my, yeah, you can. This voltage over here is mapped to this node through its GM and whatever the total resistance is here. And that resistance is pretty high. It's the R out of this device and this device, right? But then this guy goes here where the load gain is pretty low. It's this GM into this 1 over GM. So it really maps this voltage right into this gate over here. Right. And then it's like I'm driving this voltage, and again, I have GM times whatever the output impedance is again on this node. So intuitively, the two signals are sort of adding up. They're just adding up through two different paths. Okay? But we'll see that as we work out the small signal model, you're actually going to get something like that. So I'll be doing some approximations as I'm drawing this. For example, here I'm neglecting RO3. So this is M1, this is M2, this is M3, this is M4. So I'll be neglecting immediately RO3. And then I have here RO1, GM1, VGS1. And then I get RO2. And then I have my input minus VID over 2. And then on this side, I'll have VID over 2. This will be VGS1. And this will also be VGS2. And then here I'll have just the RSS. On this side up, we have the source. And then, again, the output impedance. And this will be GM4 VSG4 because this is a PFAT. This will be grounded. And then on this one, we have this VSG4. Now, I'll do this analysis in two parts. So one, just like we do with all the amplifiers, I mean, we could go and look at the voltage gain, but we could also split it and just look at the output impedance as one task. And then as another task, I look at just the total conductance or transconductance from the input to the output. That was this capital GM, right? For that, I will assume by definition that the output is grounded, and I'm looking at IO differential. So my GM differential mode would be IOD over VID, given that VOD equals 0. All right. So I'll first look at this current, because it's sort of a little bit easier for me to analyze things in terms of the current. Now, I can do two approximations here to sort of arrive at the same result. One, as I said, given that I could potentially, in the differential mode, disregard RO1 and RO2. So if I do that, then what's happening is that this voltage is Vs. Then VGS1 is VID over 2 minus Vs. And VGS2 is VID, minus VID over 2 minus Vs. So I can play the same trick that we did last time and just say, well, assume Vs equals 0, right? So if Vs equals 0, then I'll have perfect balance here. So my VGS1 is minus VGS2 equals VID over 2. Okay. So in that sense, this current from the current control source is the same as this one over here. And if I neglect the ROs, the current will flow here and not through RSS. Okay. Then I RSS equals 0, and that equals Vs over RSS. Do people understand this? So it's the same thing we did essentially for the symmetric thing. It's just that in the symmetric one, I didn't have to really neglect these two necessarily, because I had symmetric loads on top. Okay, so everything was perfectly symmetric. And I could say that really this current is going down, but the RO currents are also matched. Okay. So in this case, I'm neglecting a little bit, so simplifying, but it'll turn out that it's OK. So if this is really true, then I can really treat this VS node simply as AC ground. Okay. Still, even though the circuit is not balanced. And if I do that, then I know what this current is, because it's mostly dominated by this GM1 VGS1. RO1 will be lumped with 1 over GM3. That's really negligible, right? So the voltage that I'm going to get at VSG4 is going to be VID over 2 times GM1 VGS1. Sorry. This is going to be GM1 times, and VGS1 will be VID over 2. And that goes into 1 over GM3. And OK, so now we're here. And then that turns into this current over here through the VSG4. So I multiply by GM4. And then, since this is the opposite, current is the opposite sign of IOD, I'll add a minus sign. OK, so that's how this VID would map all the way to IOD. The other path is actually way simpler, because I just have minus VID over 2. And I'm assuming that primarily this GM2 VGS2 is really contributing. So the other part is just plus GM2 times minus VID over 2. This is in the same direction as IOD, so it's a positive sign. Okay. Assuming that M3 and M4 are identical, and we should state that here. So M1 and 2 and then separately M3 and M4 are identical. So then we can essentially cancel these two out. And because M1 and M2 are identical, we'll just write it as minus G. Okay. So now I have the IOD. Now I'm going to try to take a look at what the so I have my GM differential mode is equal to just minus GM1. So now the question is, what is R out? Okay. So just to get back to here, another way to do this analysis, instead of assuming or analyzing this to basically say that Vs is a negligibly small voltage. You could also say, and this is sort of what's more done in the book, is saying, okay, well, my RSS is pretty high anyway. So what's really happening is that this current is, I'm just neglecting any current that goes down. And so all the current is just going around. And so the part of the down current here goes here, and then also shows up over here. And that relates the down current component of IOD to what gets mirrored across. And what gets mirrored across, that means that this current that got mirrored, we can call it I down, is now also being mirrored over here. Right? And then the only difference is really kind of this part over here. So that's another way to see how things add together. It's, of course, a little bit more involved than just what I wrote here, so I don't want to do it. I'll do it, the more involved thing for the R out, because you sort of cannot really avoid that. So does anybody, I mean, even for R out, we can kind of guess what the solution is going to be. Again, it's a little bit hand-wavy, but a lot of things in circuits are like that, and then you kind of arrive to the right approximation. So I'll first guess, or have you guess, and then we'll derive it. So just you can prove to yourself that it's something like that. We've looked a lot at how things look like when you, in terms of R out, when you look into the drain of the transistor. So you're looking at some arrangement like this. There's a transistor. It has some resistor here. And then you're looking from here, right? So this is sort of happened in a lot of different places. In Widler, in Wilson, in Cascode, in a lot of places so far in the course, right? So, and we said, what is this R out? Okay, so we said it was, you know, after we cut out many terms that were kind of unnecessary, we were kind of saying it was something like this, right? And that was assuming that this R is actually pretty big. Okay, there were a few other terms that we cannot necessarily neglect. For example, if you look at the real thing, you would have something like RO times 1 plus, you know, GMR or something like that. Okay, so this one, and there was some other terms, but this one is kind of going to be critical for us in this case over here. And now, if you take a look at this circuit over here, if I say I don't care what happens with this branch high up, so I'll try to estimate my R out by looking down and then looking up. Okay, so if I unplug this branch and I'm just looking down, what do I see? I see a transistor. And what's in the tail? Which resistance is kind of at this node Vs, if I look this way? Okay, come on. First one that I see is what? Okay, great. And then if I look up over here? When you look at the source of a transistor that is like common gate, what do you see? 1 over GM, right? So I would say, okay, there's something in the drain up there, but like it's roughly 1 over GM, right? Okay. So that means that this would be RSS in parallel with 1 over GM. And I'm saying already RSS is the output impedance of a current source, right? So that should be pretty high. So I can approximate this with 1 over GM. So then this R out is RO 1 plus GM times 1 over GM, which is equal to 2RO. Okay. Okay. So let's take a look what would we really get when we kind of get into the messy math. So keep this 2RO in mind, right? So what do we have? We're going to have 1 over GM3, which is what we had previously. We're going to get our current source here, RO, another current source. RO2, VGS1. And in this case, since the gates are going to be grounded, because I'm looking at the output impedance, I'm doing like a V test here and looking at I test. Let me just mark this so that it's a little bit clearer where the I down and I up is coming from. Okay, so this is VSG4, GM4, VSG4, RO4. Okay, so this is the whole thing. And I'm going to write these labels slightly differently, because I'm going to say this node is VS. And since the gates are grounded, this really is going to be, since now VGS is minus VS, this is minus GM VS. And then this one also is minus GM VS. So I'm trying to simplify things a little bit. Okay, so we're going to label this I down, and this current, it will be I up. So I test will split into these two currents as it's going into the circuit. And so let's follow this I down. As it goes through this parallel structure, it has to come out here, because there's no other way. So this is I down. So if I assume that RSS is a lot bigger than 1 over GM, which is sort of what I should be seeing up here, I can also assume that this current is going over here. Right. So let's write out some equations. So for I down, the first condition is going to be that V test minus VS over RO1, that's the current, RO2. That's the current going through this resistor RO2. And then this current minus GM VS. So that's the KCL on this node over here. Another one that I have is what is happening over here. If I'm pushing I down over here, then this current that goes into GM 1 over GM3 is also I down. Okay? And I'm just trying to figure out how that relates to, again, minus GM VS. So here I have VS minus whatever voltage 1 over GM3 develops with I down. So it's I down over GM3. And that divided by RO1. So that's the current that flows through RO1. And then I have plus GMVS. GM1. Yeah. because minus GM1 Vs is in the opposite direction of I down. Okay. So if we try to solve from the first one by Vs, because Vs is something we don't know, okay, what we're going to get is that I down times 1 plus 1 over GM3 RO1. So that's this piece over here. And that divided by GM1 plus 1 over RO1. Okay, see if I did this right. Yeah. So now we can sort of approximate a few things. In this case, I can say that 1 over RO1 is much smaller than GM1, right? Because it's the output impedance. And GM3 RO1 is 1 over GM3 RO1 is definitely smaller than 1. So I'll just approximate this as I down over GM1. Okay. So once I have this, I can roll it back into the other equation that I have for I down. So I'll take this Vs and move it over here. So I'll get Vt over RO2. And then I'll have, instead of Vs, I'll have minus I down over GM1 times GM2 plus 1 over RO2. Okay. So again, 1 over RO2 I'll neglect because it's a lot smaller than GM2. And from this, I get that I down 1 plus GM2 over GM1 is equal to Vt over RO2. What is GM2 over GM1? So 1. Right? So I can't neglect that. So my Vt, or my I down, is Vt over 2 RO2. Remember that 2 RO2 that we just did for the cascode? Well, that's this thing, right? That is the resistance we're seeing when we look down. Okay. So we sort of made some similar approximations to when we just did the inspection analysis. But sometimes it's also useful to just go through a little bit of math to persuade yourself that that's correct. But as you'll see in the next step, for some of the things, you have to be very careful which things you kind of neglect at what point, because they may prove to be crucial in the end, where you're subtracting two things that are very close to each other and looking for the second order effect. But in this case, this is the I down. Okay. So let's take a look at what I up is. As we've analyzed here, just see what I marked here is, if I down is here, it will be mapping here as this little I down. So what we see, we have is that I up is I down because it got mirrored through this voltage-controlled current source. And then we have this extra nuisance over here, which is Vt over RO4. That's the output impedance. If you plug in the expression for I down, this is, again, Vt over 2RO2 plus Vt over RO4. So this is this feedback part. This is sort of what got mirrored from this I down all around to this one to turn the current source effectively into the same 2RO2 kind of output impedance, right? So if you take a look then at IOD, which is I up plus I down, you get Vt over 2RO2 plus another Vt over 2RO2 plus Vt over RO4. Right? So if we take a look at this diagram, looking down, we have 2RO2. That same thing gets mirrored all around. So looking up into this current source, we see another 2RO2. And then we see RO4. Right? So we're really seeing here Vt over 2RO2 in parallel with another 2RO2 in parallel with RO4. And then, of course, that is just RO2 in parallel with RO4. Okay. If you knew the result, you could have sort of reasoned that if you look at this, neglecting or making that RSS is so much greater than 1 over GM, kind of like what we did earlier on with this, assuming that Vs is going to be sort of balanced between the two gates. You're sort of then again guessing like, okay, well, what if Vs was really like a negligible voltage, meaning that the negligible signal was flowing in terms of voltage was all around here. Then, if I looked from here, I would have really seen essentially just this RO2 in parallel with RO4. Right? So the currents from these two sources would be taken out. Okay? So that's sort of another way to look at it. Okay. For common mode, it gets a little bit tricky. So let me just first finish the ADM. So our differential is, by definition, minus GM differential times R out. And by GM differential, we got minus GM1. And then times R out, which was RO2 in parallel with RO4. So this is GM1, RO2 in parallel with RO4. Now, just to double check the signs and everything, if you go back to your amplifier, okay, one more. What is the phase relationship between VI1 and VO? Okay. How do you look at that? What is the... Okay, so let's analyze that. That's a very important thing to analyze, as you saw, like with negative and positive feedback, if you don't get your signs right, you can start moving around, right? So what is the relationship between gate and drain in any transistor sort of common source amplifier, and whenever you're looking at how signal propagates for voltage from gate to drain? If gate increases, the drain current increases. So because there's some impedance attached, what is going to happen with the drain? You're pulling more current, so drain has to go. It's like Caesar, up or down? Where is it going? It's going down, right? Because all this is like one resistor, right? And you're pulling more current from it. So this node has to go down. Okay, so this node is going down. That node is also directly driving this gate. So if that node is going down, where is this going? Up. So then these two are in phase. Right? Another way to think about it is always between gate and drain, there's always a pi phase shift. So I get pi, and another pi is 2 pi. And then between this gate and this drain, I get pi. So if I'm defining my input as VI1 minus VI2, then my total gain has to be positive, the way I've organized the circuit. Okay? So this is just a useful thing to always kind of keep in mind when you're checking the calculations, because I may have gotten my signs wrong. Okay, so this is the differential mode. Let's take a look at the common mode. So in the common mode circuit, I don't have the inputs grounded. So I'll have my 1 over GM3 RO4 and then I have the two inputs that are each VIC. And then again, because I know my R out, the only thing that I need to figure out what is the transconductance as I'm going out. Right? So what I need is, so A common mode will be minus GM common mode times R out. So I already know R out. I only need to find now what is the GM common mode. So for that, we're again going to put this current, IOC in this case. And we have I down and I up. GM2 VGS2. In this case, it's a little bit more complicated because VIC is now not 0. And this is GM1 VGS1, RO1. We connect these two. And then this is VSG4. GM4 VSG4. So looking at I down, again, I down shows up over here. That's not an approximation. That's exact. Right. But this time around, because I'm moving VIC up, I can't really say that I'm balancing around this node VS. Right? This node is also going to be moving somewhat around. Right? So in this case, I actually cannot really neglect what's flowing or the current that's flowing through RSS. Okay? So what I can do, though, is say that, look, whatever, because this is 0, and this is 0 over here, then really nothing's going on through this RO4. Right? So all my I up is coming from this GM VSG, which means that all I up is flowing here as well. If I up is in this branch, it's also in this branch over here. So now you see why I can't really neglect what's happening with RSS. The only difference between I up and I down is really because of this RSS. Right? If this RSS didn't exist, my I up will be equal to I down. And then what would happen? What would be my common mode gain? 0. Right? Or I up will be minus I down. But basically, there will be no IOC. Right? And there's no IOC, then there's no GM. And yes, indeed, in that case, if that was really true, you would indeed get that the common mode gain is 0 and common mode rejection ratio is infinity. Okay? But because of this RSS, it's kind of ruining that perfection. Right? So we have to take it into account. So we'll write that we're looking at around this node that I down equals VS over RSS plus I up. And then we're going to do just a few tricks, just like we did for the. We're going to look at KCLs kind of at these nodes to be able to write out a few more equations for I down. So, for example, we're going to do I down is minus VS over RO2. So we're looking at current in this branch and then this branch over here. plus GM2, this is VIC minus VS, which is VGS. So we did the KCL for this node. And then for I up, we're going to do KCL on this node over here. And that's minus GM1 VIC minus VS. So that's this current. And then we have the current through RO1 plus VS minus I up over GM3 over RO1. So from this one over here, we get that I up is, or let's write it a little bit differently. I up 1 plus, let's move this, 1 over GM3 RO1 equals minus GM1 VIC minus VIC, and then plus GM1, now we're regrouping the VS, plus 1 over RO1 VS. Okay. If I take this top equation and I rewrite it as, I rewrite it as GM2 VIC minus GM2 plus 1 over RO2 times VS. These two are exactly the same, just the opposite sign. Okay? So I can say that I up 1 plus 1 over GM3 RO1 equals minus I down. So this is where our difference is, right? The fact that we didn't neglect what was happening with VS. Okay, so let's start from that equation again. If we plug that back into the first one we wrote, which was this simple one around the RSS node, so we're going to repeat that just so we have it. So from this one, we get that VS equals RSS times IDN minus I up. Right. And then, of course, we know what the relationship of I up and I down is. So we'll say that this is minus RSS 1 plus 1 plus 1 over GM3 RO1, and that times I up. So we have that from the previous one, I up times this factor 1 plus 1 over GM3 RO1 is minus GM1 VIC, and now we have the factor that was due to the VS, so that would be minus RSS 2 plus 1 over GM3 RO1, and then times whatever was on the previous page, this factor over here, GM1 RO1. And then we have I up. So from here, if you move things around, you get 1 plus 1 over GM3RO1 plus this whole thing over here. And that is GM1 plus 1 over RO1 times 2 plus 1 over GM3RO1. And that times RSS. And that equals minus GM1 VIC. So now that I'm here, I can try to make a few approximations. Okay. So for example, this 1 over GM3RO1 is definitely alone with respect to this. I can cancel it as being much smaller. Then as I'm doing these multiplications, I get 2 GM1 times RSS, so I'll have to keep that. RSS is a pretty big value. And then I have GM1 over GM3, and then RSS over RO1. So I can sort of neglect that. I mean, I can keep it, but it'll eventually 1 over RO1 is much smaller than GM, so I'll just take that out. And pretty much out of this whole thing, this is all that remains. But you see, it was important that we did not neglect what was happening around RSS, because if we did, then this factor would be gone. Okay. So now we have that IO equals I up plus I down. And we can write and that is because of this. When I cancel this one, then that will just be minus I up times 1 over GM3RO1. You see, it was also important here that I did not neglect this piece and say that I up equals I down. Because if I did, then common mode rejection ratio will be infinity, right? So, and this is then equal GM1 VIC over 1 plus 2 GM1 RSS times GM3 RO1. Okay? So then our GM, common mode, will be equal to GM1 over GM3 RO1 times 1 plus 2 GM1 RSS. Now, as we said, ACM is minus GM common mode times R out. And CMRR is a differential mode over a common mode, because both are just GM in differential mode times R out, and the other one is GM in common mode times R out. Then R out will cancel out. So if I'm just looking for common mode rejection, I don't even need the R out, because it's the same in both situations. And then this would, of course, be what we had previously, which was GM1 times RO2 in parallel with RO4 over GM1 over GM3 RO1 1 plus. Sorry, we don't need this. This is just GM1. 1 plus 2 GM RSS. Right. So these two go away, and then your CMRR is really just GM3 RO1 times 1 plus 2 GM1 RSS. So this means the better the current source you can put, the higher output impedance you can put in the tail, the better supply or any common mode rejection you're going to get in your amplifier, right? By this amount. But it also tells you that unlike the one that we did previously, which was just a nicely balanced diff pair, this one has sort of an inherent, it has an inherent common mode rejection that depends on RSS. Right? Okay. Okay. So let me just kind of set up the next lecture where we're going to look at the offset by talking a little bit about how it looks like in the transfer curve. So this is the VI differential. This is the VO. And if you look at what we sort of did already in context of biasing, but if you look into just the transfer function, for a diff pair, we would expect something that looks like this, where we said that this was kind of the input range, and after a certain input range, the current will swing all the way to one branch or the other, and we would have no dependence between input and output anymore. So that's called my diff pair got saturated, right? It got swung or one way or the other. So all the amplification is really happening in this range. Now, with offset, that just means that we've added something here that has shifted the point at which V output is 0. So now, no longer is my V output 0 at when input is 0, but it's 0 at some other point on VID. So I have something that looks like a parallel curve like this. This point here is VID equals V offset. Okay. And we'll be looking, so this is called input referred offset. This is VID at which VO equals 0. Okay, so by definition, offset is going to be the input voltage, or input referred offset is the input voltage at which the output equals 0. Then we're going to go and sort of derive what that means in the context of the differential pair and how that imbalances kind of everything that you do and calculate about it. Okay, so that's all for today, and we'll continue on Monday. I have your homeworks, by the way, so if you want to take them.